So in this video, we are going to look at the code of this memory optimizations and see what's going on there. So at the beginning of this optimization, we are going to look for the local allocations that are promotable. So a local allocation is promotable if this location is only used as the pointer of the load and store instructions. So if it is used in other ways, it will not be promotable. So this is basically the collection of the locations that is not promotable. So how to populate this by looking at all the instructions, and if it is used as, for example, the LHS or RHS, the binary operation, we are going to mark them as impromotable. So we are basically collecting all the operands that is used as we are collecting all the operand that is also a local allocation that is not used as a store or load. So this is fun, right? So in the store instruction, we are going to mark the value as impromotable because the pointer value is leaked to the memory. However, if it is, however, for the pointer, if it is not, for pointers, we are not marking it as impromotable, and instead we are collecting the block IDs for which the stores are happening. So for each local variable, for example, say %L, we are going to add we are going to collect the block IDs for which a store instruction to the location is happening. So it is just the code for deducing that. As I said, the load instruction as pointer value is not marked as impromotable because even though a location is loaded, it can be promoted. So if it is used as the function pointer or argument, it is not promotable at all, and it is also used as typecast, then it is not promotable. So after doing that, we are collecting the set of impromotable locations and the block IDs in which the stores are happening for each local variable. So if everything is impromotable, then we are going to just bail out. We cannot do anything. We are not promoting anything and go return false. Otherwise, we are going to draw many things. We are going to draw the control flow graph and the reverse of the control flow graph. So if, for example, if B1 jumps to B2 in CFG, then we are going to say B2 has an edge toward B1 in the reverse CFG. So this is basically the meaning of this reverse CFG. And it is used in the construction of the domination tree, which we are going to see later. Okay, so far so good. So far we are constructing the control flow graphs and the reverse control flow graphs and the domination tree. And then we are going to calculate things for the memtrage optimization. So the first thing to do is we are going to calculate the potential blocks for which fine node should be inserted for each location. So here is the trick for this. So for we are going to iterate over all the allocations here, and we are only going to consider the allocations that is promotable because we are promoting locations. So we are only need to consider only the promotable locations. And here the BIDs are those blocks in which the store store is executed for the allocation AID. So this is BIDs are the block IDs for stores, and we are going to perform some graph traversal to see where we should input the finals potentially. So these BID frontiers are basically the frontier of a block here. So here in this iteration, we are going to basically doing some DFS here because we are using a stack here, and we are reaching to the dominance frontier of each block here. So we are basically constructing the this dominance frontier of X union, dominance frontier of X union, blah blah blah, where X is the set of blocks in which a store happens, store to AID happens. So this is basically the meaning of X, and we are going to calculate this dominance frontier of X union dominance frontier of X in union blah blah blah. So this is basically that, and as a result, this joins is the potential positions, potential blocks for which the final should be inserted for its allocation. So this is allocation ID, and we are going to calculate for each allocation ID the set of block IDs for which final should be inserted potentially. All the other places should not be inserted with the finals for the corresponding allocation. So that's the meaning of that. And this is a special data structure we are going to construct in the course of finding the join point here, but I'm going to explain it later. And this is what I'm calling a replacement dictionary. So this is basically recording the fact that, oh, this register ID should be replaced with some operand, for example 42. For example, the %x should be replaced with %y, for example. So such a replacement information should be recorded here. And this final indexes means that so this joins means that potentially here we are going to insert some finals, right? So it is not yet decided that we are going to insert such finals in here. But on the other hand, final indexes are those positions for which we are committed to insert finals. So this AID here and BID here, this is a pair of allocation ID and block ID, which means that for this allocation, we are going to final at the head of the block here. So we are going to collect a set of such information that records our intention to insert finals. And furthermore, this is what is called end values, which is recording the last value of that is stored for each promotable locations. For example, if AID, BID is pointing to some value X, then it means that for the allocation AID, and at the end of the block named BID, the AID should be stored with the value X. That's the meaning of that. So it is collecting that information, which will be later used as an argument for finals or the value to be replaced with for the load instruction. Okay, so far so good. So they are such variables, and we are going to iterate over the entire code, we are iterating over the blocks and we are also iterating over the instructions. So we are considering every instruction inside a function basically. And we are only interested in store and load instructions. So other instructions, we don't care. We just leave them as they were. And if it is a store instruction, we are seeing if it is a promotable location. So if it is a promotable location, we are updating what is called the end values, which records the last value for each allocation and each block. And we are basically updating here the last value of this allocation ID and block ID should be this value. This value is the one that is being stored during this instruction. So it can either be a constant value, for example 42, or it can either or it can be the register, for example ampersand t or ampersand t2 or etc. So we are recording that information inside it. Okay, so far so good. And what is happening for loading instruction is a little bit more fun. So we are again only considering the promotable locations. Otherwise, we just continue. We are just ignore them. And if you are encountering a loading instruction, then we first look for the join BID, which is basically the I mean, which is the nearest nearest block where a phi node may be inserted at from BID. A phi node for AID may be inserted. So, okay, maybe you can. So it is the nearest block from BID where a phi node for AID may be inserted at. So, okay, so it is a little bit dense. So, but it is not that very. So, and these two lines of code is better explained later, but we are going to look at this first. So I'm going to first look at the what is called end values. We already discussed this. This is storing the last value that is stored in the location for the block. And if it has something, that's good because we have the nearest value, the latest value stored in the same block, so we can just reuse that. Oh, this load result should be the store value that is just stored before. So we are going to use it as a value here. But otherwise, if no store happened in the same block, then we need to look for the alternative. So the first thing to do is we are going to look for the blocks for which a phi node may be inserted, right? So, and we are going to find the nearest one because that will be the value that should be propagated to the block. So the BID join that is calculated here is basically the block ID of the phi node that should be valid in the block and at the beginning of the block BID. So that is the meaning of that. And we are going to look at this join table later. So for now, let's assume that this is just the phi node, the block containing the phi node that is valid for the BID. Okay, so far so good. So if this BID joins end value has something, then that's okay. We will use that as the our value. So this will be the load result. But otherwise, we need to insert a phi node at this point. So we need to insert a find node at the BID join. So that's the reason why we are inserting this pair into the find node indexes map. And we are going to say, oh, this load should have the value of the find node. The find node is for the allocation AID, and this find node is inserted at the beginning of this BID join. That's the meaning of this operand variable phi, blah blah blah. A find node for this allocation ID that is inserted at the beginning of this BID join. So there are three layers of values. So it has an AND values. If this block has AND values, we're going to use it. Otherwise, we are going to look for the nearest block for which a find node may be inserted, and we are going to use the AND value of this BID join. And if it doesn't exist, we are going to insert the find node at this point, and we are going to use it as the value. Okay, so far so good. And we are going to insert this pair into the replacement dictionary. Oh, this is the register for this load instruction. So this is basically holding the load result. And we are going to say that this load result should be replaced with the value here. It is calculated here. Okay, that is basically the thing. We are overall in these iterations, we are going to scan each block and record the latest value here, and we are going to deduce the which value each of the load result will be. So we are going to replace each load result with this variable here, and it is calculated in this way. Okay, at the end of the day, after finishing scanning the code, we are going to actually insert finals. So these are the finals that is needed for the load results, but we may need to insert more finals because this final should be populated with the other finals. So load results may be replaced with finals, but this final in turn may need the value that is also a final, another final basically. So we are going to search for all the finals that is necessary to be inserted by a traversal here. So we are going to use DFS here basically because we are basically manipulating a stack here. And here we are going to look at this. So for each find node that should be inserted, that is here. So find node for this allocation ID, AID, for the block ID, BID. And we are going to look for the predecessors of this block. So this block may have multiple predecessors. So we are going to consider all such predecessors. So we are iterating through all of them, and let's say BID prev is one of them. And this is the pair of allocation ID and a previous block ID, and we are going to look for an AND value here. And if it exists, we are going to use it. Otherwise, we may need to look for the find node that should be inserted here. So at this point of time, if AND values has no entry for this AID and the previous block ID, then we need to look for the Again, we need to look for oh, this is wrong.